Hello, everyone.
Hello.
Welcome back. Yeah, so we're still here at C++ Russia, and today we have a great talk, getting the most out of GDB. And we have Mark and Greg, and actually we're going to discuss advanced features of GDB, more than just, breaking, stepping, and printing. And you can actually count how many new tips you learned today, and maybe we can even play, some kind of a tips quiz later based on the talk. So we'll see. So our speakers today, Greg Law and Mark Williamson from Undo Company. So Greg is a co-founder of Undo, CIO and CTO, and he carves out what time he can to write code and debug that code, although sadly that isn't as much as he'd like. He holds a PhD from City University of London. And Mark has worked at Undo for 7 years, and as software architect, he works to optimize both software systems and the human systems of the engineering organization. So welcome to C++ Russia. We're really happy to have you here. And I just want to briefly remind to our listeners a few words about our format. So you can ask questions in the player or in the Telegram chat directly. So both ways are fine, and really encourage you to join the discussion in Zoom after the talk. But the important note is that we'll have a few stops during the talk for the questions. So if you have any kind of question, please throw it to the player or to the Telegram chat, and don't wait till the end of the talk. So we'll handle a few questions while we're running the talk. And now, so I actually have first a small question to Greg. So since you're with Undo for 20 years on some kind of this, leading position, CTO, and all these titles, so how often do you write actual code in your position, and maybe you're missing it, or maybe you have some pet projects? So how do you cope?
Yeah, I do get to write a little bit of code, but yeah, not nearly as much as I would like. It might be on a rainy weekend or something, or maybe I carve out a little bit of time. So I've not been with Undo for 20 years. Company's not that old, but it has been nearly 10 years now. Obviously, as in the beginning days, it was just coding all the time, coding. But as the company grows, you get less and less time for that, which is kind of frustrating because it's still the most fun part.
And do you use the debugger often?
Yeah,
in your pet projects?
Absolutely. So I mean, I write more bugs than code, so I spend a lot of time in the debugger, and we do a lot of eating our own dog food. So we have this awesome time travel debugger, which especially when you code as seldom as I do, you need all the help you can get, right? So I spent quite a lot of time when most of my code was written on airplanes when I was traveling around a lot. And I found that was a really good way to make, if it's an 11-hour flight to California, a really good way to make that go quickly, much better than watching a load of, how you can watch 5 films in that time or something, right? I can't watch 5 films. But if you just write code, it makes the flight go a lot faster. But of course, there hasn't been the same kind of travel the last couple of years, so I've had to carve out different times to do that.
Yeah, right. I think we all write more bugs than code. Just one person can actually say that, yes, that's true, and start the debugging, and the others are just, continuing writing bugs, not code. Mark, actually, one question to you as well. So I find one interesting fact in your beard that you're trying to climb tall things and not trying to fall off. So my question is, what was the tallest thing you actually climbed?
I think the tallest thing I properly climbed was some cliffs in Wales, in the west of the UK, which was very much one of those situations where I signed up for a climbing course, got talked into being on the more advanced one, and then found myself sitting on a ledge about this big, looking out over a valley and thinking, am I allowed to be here?
How high were you, Mark, at that point, do you think?
I was probably 100 meters up, but I was sitting on a piece of rock that was only just large enough to park myself on, and dangling my legs off the cliff, which was a strange. I could see a train going across in the foot of the valley, and it looked about this big. It was quite strange.
My tummy feels a bit funny just thinking of doing that.
Yeah, actually, the whole image reminds me of the whole debugging process. You're sitting on some rock or some cliff. So that's very much the same. And with that, I think that's a good segue to your talk, Craig. So let's go for the talk now.
Awesome, thanks. Yeah, so we're going to, as Anastasia said, we're going to talk about getting the most out of GDB. So yeah, I mean, and also as Anastasia said, we all write more bugs than code, right? I mean, I like to think of myself as an okay programmer, and how many lines of code? You think about how many lines of code can you write without a single bug, like of any kind of reasonable complexity. I mean, I think if I'm honest, like maybe 20 if I'm really concentrating, right? It's just really, humans are not very good at writing code, and most of what you're right, most of coding is not typing the code in. Most of it is figuring out what the hell is it doing, right? Maybe it's not code you wrote, maybe it's code somebody else wrote, but just a huge part of the job is figuring out what code did, and debuggers can be extremely useful in helping us to do that. So I'm just going to make a disclaimer at the beginning. I don't consider myself to be an authority on GDB. There's still lots of bits of GDB that I've never used, and I suspect even more that I don't even know about. But I have learned lots of things along the way, whether it's making our own product, which has a GDB interface onto it, or whether it's working with customers and helping them with their issues. I've learned a bunch of tricks along the way that I think are useful. The purpose of this talk is not that you will listen to this talk and come away being an expert in all of these things and able just to do all of these things. The thing is the point is to let you know that these things exist, right? And then maybe it's 6 months time, maybe it's years time in the future, and you're stuck on a problem and you're trying to get to the bottom of it, and you think, I remember there's a feature in GDB that might help me do that. I'm going to look up in the documentation, look at the info pages on GDB they're pretty good, right? They're pretty complete, and they're mostly accurate, but they're not like the rest of GDB. They're not discoverable. So the thing is to know that this stuff exists. Once you remember it exists, you can go find it and look it up and see how it works. We'll do a bunch of demos on a lot of it as well, so that you can kind of, it helps you kind of understand exactly how the stuff all works. And maybe you can come and look at this talk on, when you're trying to do it, you look at this talk when it's up, when the video is up, or alternatively, we have a whole bunch of sort of 5-minute little tutorials, a thing we call GDB Watchpoint. That's on the undo.io website, and I've done a bunch, and Mark, who's with me, has done a bunch as well, and they're little, bite-sized tutorials on certain topics. So a lot of information there, but we'll try and cover lots of stuff. So this is kind of quite broad and quite shallow, right? So yeah, I mean, as I said, right, the documentation is like GDB itself. It's very rich. GDB is very powerful, but it's not very discoverable. And so I like to make the distinction between easy to use and easy to learn. It is actually quite easy to use when you know what you're doing, but it's not easy to learn. There are good front ends to GDB. There's graphical IDEs. VS Code is seeing a lot of use at the moment. CLion, I think. I mean, I'm not just saying this because Anastasia's on the call. CLion, I think, has of all of the IDEs the best integration with GDB, so it has full support for things like watchpoints and other things that are kind of lacking, I think, in most of the GDB front ends you get. So a little bit more discoverable from these IDEs, but there's still a lot of power underneath, and you kind of want to drop down to the prompt to get that power. So that's enough kind of intro. Let's get into some stuff. So TUI, usually called Tui Mode, stands for the text user interface, right? So like a graphical user interface, but text-based. Well, you might think, well, isn't GDB always a text user interface? Because if I go, here's my little Hello World program. Hopefully we can all read that. So I'm going to do the usual thing. I'm going to compile the code. So here's a little thing. You might compile with -G. I like to compile with -G3. That gives you a bit more debug information. The debugger can understand macros and sometimes do a better job of debugging optimized code as well. The debug info is a bit bigger, but other than that, it's a good thing to do. So gcc-g3 hello, and then I do my GDB thing as normal. So I mean, this is surely a text user interface, right? It's just a whole bunch of text. I'm going to start my program. You may not know that the command start is effectively all it's doing is putting a temporary breakpoint on the function main and then doing a run. So that just saves me a little bit of typing. Okay, start. So here I am. This is the classic GDB interface that we all know and maybe or maybe not love. Of course, I can look at the code with lists. It's like, yeah, okay, that's kind of all right. But it's not. If I've only got an 8-line program here, so it's not too bad. But if I've got a real program, obviously it's hard to kind of navigate. Where am I? Looking at matching up line numbers and things. But if I go layout source, I'm going to go into Tui mode. Tui mode is, I think, in my opinion, it is the thing that kind of scores the best on both metrics of what is least well known and most useful. It's an extremely useful interface, and in my view, surprisingly few people know it exists because GDB is not discoverable. If you only use GDB a few times a year, you may not know it exists. So layout source, I hit enter, and voila! Right. So now I have the text user interface, Tui mode. And I can obviously it's a tiny program, and you can see here I've got a nice bit of syntax highlighting. That's because this is a relatively recent version of GDB. I think it's a GDB 10 I'm running here. And if I do a next, I can still type it in the console here as normal. Do a next, and of course it will move forward one line of code. Great, right? Except, of course, the only thing. Look, it's messed up my terminal here. It says the word world. So anything that my program prints out is going to print out into the terminal. And it's a curses program, so there are other ways to cause it to just break, right? I haven't found any reliable ways to make it to break it, but it does break from time to time. So I'm going to just go Control L, and that will repaint the screen for me. So when you get stuck, Control L is a useful thing to do. I can scroll up and now. One thing that can be annoying in Tui mode, if I go the up and down arrows, right? So obviously, I'm sure you know, I can press the up arrow, and I'll usually get the previous commands in my command history, right? Save me doing a whole bunch of typing. But if I'm in Tui mode and I do up arrow, well, I'm at the top of this. I'm at line 1 here, so nothing happens. But if I go down arrow, you can see, look, I just get scrolling down. If I go up arrow, it scrolls back up. So if I want my previous commands, it's a read line, GNU read line interface, so you can do the usual things there of Control P for previous command. I can Control P again and again, and I can Control N to go to the next command through the list. If I want to edit these commands, also I can't go left and right, because if I go left and right, it goes like that, right? So again, Control B to go backwards, and Control F to move forwards. So that just helps me edit my command history, which is kind of handy when you're in Tui mode. Otherwise, everything works pretty much the same. I can go back. The way I can switch to Tui mode by changing the layout, or I can go Control XA, which toggles between Tui mode and CLI, command line interface. So Control XA, and I'm back into the CLI. Control XA, back into Tui mode again. I can go more than this. I can look at multiple windows. So if I go Control X2, that will change what's displayed in the main window. So I've got there. Obviously, this is the assembly. If I go Control X2 again, it cycles through these different views. So now I have my source code and my assembly, which is kind of handy. If I go Control X2 again, it cycles through another mode, which I don't know why it's saying register values are unavailable there. But if I step, here we are. We've got all of the registers and the code as well. So that's kind of handy. I'm going to show you something else in Tui mode, which is in the later versions of GDB. But I'm going to show after Mark has introduced some Python stuff, which is coming up in just a moment. So that's Tui mode. There's a quick refresher. So we can type layout source to go into Tui mode, or we can go Control XA, Control L to refresh the screen if the screen just gets in a mess, which does happen, and Control P and N to cycle through command history, and Control X2 as you cycle through these different views that you might have. So on that, we're going to switch now. Mark's going to introduce some stuff around Python. So I'm going to stop my screen share and allow Mark to take over. And it's a good time. Anastasia, do we have any questions?
Yeah, thank you. Thank you, Greg. So actually, just a very basic general question maybe here right now. So we started with, stop and writing debugs and start the debugging with these all awesome features of the GDB. So, but what's the sign at which I should stop writing the bugs and start, debugging? Should I wait for some crash or something going completely wrong, or there are some, better techniques to start debugging earlier, maybe? Because I know some people are just starting, writing the code and they immediately start debugging it, and that's a way they program. So, but maybe there is something in the middle which is the best solution. So, what do you think about it?
I mean, I think all else being equal, the earlier you can fix your bugs, the better, right? There's lots of good evidence on the later in the process a bug occurs and has to be addressed, the more expensive it is. So if you can fix the bug before you even merged any code into the repository, then that's better. And certainly if you can fix bugs before it's been deployed, that's better, right? So earlier the better. But of course, in order to go fixing a bug, you have to know that the bug exists, right? Now, yeah, but I guess there is a good question on whether you want to kind of do this kind of depth first approach. When you find a bug, do you just note that bug down and record it and then move on, like to finish the feature you're doing, and then kind of have this list of bugs that I come back to at the end? I think there are times when you want to do that. I think it depends what you're doing. So if you do that, of course, what you're doing is building up technical debt. And I like the term technical debt because just like financial debt, it's seen of as universally a bad thing, but actually used in the right way, technical debt, like financial debt, can be extremely powerful. In fact, it's very difficult to start anything without some kind of debt. But too much of it will kill you, right? So you need to be really careful. It's one of those things that sort of grows exponentially, a bit like a pandemic. And the earlier you get on top of it, the better it is. So there are times when technical debt is desirable. If you're just experimenting, you're trying to make a demo really quickly. You're in those sort of early phases of a project where you're just trying to kind of prove that something works, and then technical debt is valuable. Once you're beyond that point, once you know this is actually the right thing for me to be building, and I want to ship it and make it work, then you kind of you don't want to be building up technical debt. And the earlier you can fix things in the process, the easier it's going to be.
I'd actually just butt in as well. An alternate take on when you should start using the debugger could be before you've written any code, because obviously you can't use it before you've got a program, but usually you're contributing code as part of a larger project, and shouldn't be underestimated how much you can use a debugger as an understanding tool to figure out the mechanics of how the process you're going to be working within actually functions, and make sure you properly understand it in your own head before you start calling those interfaces.
Yeah, right. Thank you. Thank you for the amazing answers. So, okay, Mark, I think we can proceed with your part now. So let's move on.
Thank you. So I'm going to talk a little bit about Python in GDB. I think around GDB 7, the GDB developers integrated a Python interpreter. And what this means is actually you've got the full power of Python available in GDB for scripting. And you've also got the whole Python batteries included standard library. So you can do kind of arbitrarily powerful things to customize your GDB session. Kind of headline is, how do you get into Python? Well, if you've got a one-liner you need to do, and you might use this to do, some maths, just do some computation on the command line, or call a function that you've defined earlier, the Python prefix tells GDB to feed the rest of that line to the Python interpreter, and that's just a one-shot. If you want, the Python interactive command will actually spill you into a Python prompt like you get if you ran Python 3 on the command line, and then you can do interactive Python exploration, basically, so you can import modules, call functions, see their results, manipulate them, just as you would in a normal Python process. The other thing you almost certainly will want to do as you put down more advanced Python code is save your Python as a script full of debugging helpers and source it in. And the normal GDB source command that you'd use for a GDB command script will see the .py extension and automatically feed it to the Python interpreter. So you can just seamlessly import a script of helpers. Got a few examples of how you'd use Python coming up, but first, let's just talk about the fundamentals. So your distro's Python almost certainly has, your distro's GDB almost certainly has an integrated Python, and depending on your distro, it might be exactly the same Python that's the default distro Python, or it might be a separate one for GDB. But it should have access to all the standard libraries. In addition, the embedding in GDB provides an implementation of a module called GDB, which you get to by typing import GDB in your script or in your CLI session. And that gives you access to some special source that you can use to automate GDB's behavior. So probably the most important function in that module is gdb.execute, and that's going to just do GDB commands you specify on the command line. So in particular, you're passing this a string argument that you might have generated using Python string formatting, and it can be anything that you type in at the GDB CLI that Greg showed earlier, and it will cause that to execute within GDB. And if you want, it can also return GDB's output as a string that you can post-process in Python. So you'd use this to automate, in simple scripts, or you might use it to access obscure bits of the GDB user interface that aren't exposed via dedicated Python bindings. The next important function to cover is gdb.parse and eval. And this is analogous to the print function in GDB, where interactively you might say print and a variable name, and it will give you the variable name in a form that you, the human, can understand. Parse and eval is the equivalent of that for Python. So you pass it a string, which is an expression in the language you're debugging. So C and C++ for this audience, but other languages are available. GDB does support debugging all sorts of languages. And what it's going to do is whatever expression you specify, if it's just a variable, it will go and get that variable value. But you can also specify more complex things, indirecting through pointers, subscripting arrays. And GDB will figure out what that C expression means and go get you the data and return it as a Python object, which you can then operate on in your script. The final thing to note is that the GDB module does have online help, as generally Python modules do. So it's got all the doc strings, and you can explore it using help, the dir command, to figure out what's in there and figure out how to solve your problems. Now, I've got a few examples of using Python in GDB. The first one I'm going to do is how to customize your prompt. So GDB has a default prompt, which is GDB in brackets, which is great because it reminds us that we're in GDB and not in the shell, but probably we can remember that, and it's not so interesting. You can also configure it somewhat statically using the GDB commands setPrompt and showPrompt, and you might want to do that when you are using a custom set of GDB configuration to remind yourself where you are. You could also use that from a GDB command language script to provide some level of dynamic behavior. But we live in the modern world where we've got things like Powerline Shell and other niceties. Most people I see have got extremely customized command prompts that give them all sorts of context rather than just telling them what program they're using. So let's see how we can make something a bit more dynamic using Python. So I'm going to switch over to a window with some code. Now, I've got a little program here I'm just going to use to demonstrate. So I'm not going to use Tui Mode for this example. It's a trivial program. It's just going to do some work, do some maths, and then exit. What I'm going to just draw your attention to is, to start with, we have the standard GDB prompt there, just brackets GDB. I'm now going to source prompt.py. As I mentioned earlier, just source, and it will go to the Python interpreter. we can see now my dynamic prompt is activated. And I've set this prompt up to show current time of day, which you might be glad of if you're pouring back through logs and trying to figure out where you are. Also, if you're running a program under GDB, you might benchmark something this way. It's the kind of thing I've occasionally done during development. The other part of the prompt is the name of the current function. And just to show you that that's fully dynamic, so I step through this program, you can see it's updating to correspond to the function of the frame we're in. And as I step back out the function, we end up in the exit function in libc, and the program's exiting, and to the end, we've now not got a frame because it's gone, so it says no frame. Just to illustrate for you what that looks like, we are importing in the script the GDB module, which is provided by the debugger for our convenience, and we're importing Python standard time module to do the formatting of the current time. That is getting us a string for the time, getting us a string for the frame, or no frame if we're not running the program, and then it simply has to return what we want on the prompt. And GDB will call the prompt hook variable from the GDB module if we just assign to it. So it'll do that every time it wants to display a prompt to us. So that's just a quick way you can customize, but actually you can access any data you want from the program you're debugging in this. You can access global state from your system. You could put some sort of, I don't know, quotes file output in there if you want. It's Python, so you can go wild. The other topic I wanted to cover was that pretty printers. So pretty printers are a super powerful feature. What they give you is the ability to customize how GDB displays data to its user. So you can actually change how your data structures look when you're debugging in GDB to get GDB to do some of the work for you, take away some of your cognitive load. Now, one case certainly I experience a lot is that you tend to have structures in your program that track important things, and maybe 50, 90% of the fields in the structure are not interesting to you almost all of the time. So you tend to have structures with performance counters or bookkeeping information, pointers to other data structures. Usually I don't want to view those. I actually just want a summary of what the structure's really representing. And you can use pretty printers to kind of highlight the interesting values and hide boring ones whenever you want. So here we've got a really basic implementation of a pretty printer for GDB. It's simply a class that takes a value that's going to print later as its constructor, and then the toString method is called to format that value for the user. And this one is doing something really, really simple. It's just taking some sort of structured data that has a field called member, and it's just extracting that and showing that. So it's hidden effectively from the user's view all of the other fields that might have been in this struct that weren't interesting and reduced it down to the thing that was. The other thing that's just worth highlighting briefly, and the GDB documentation probably describes this better than I can, is the boilerplate at the bottom here. And what this is telling GDB is when it should use that printer, because not everything is a struct with a member called member. We're using the GDB library's regex collection pretty printer to basically teach GDB that if you see a type whose regex regex matches with my struct, then that's the thing you should call this printer for. We've registered it, and now every time the user tries to print this, they'll see the post-process version produced by this class. So I've got a couple of examples of pretty printing in action to make it a bit more concrete. The first one I'm going to show you is a slightly more complicated version of what we've just seen. So in this example, I think I'll actually just start this in Tui mode, and you can look at the source code there. Our programmer has defined a value t structure, which contains one unsigned, which has got some data in. That's the value of interest. And it's got a canary field as well. and they're using the canary field to decide if one of these values has been correctly initialized or not. So we might use this to detect memory corruption or data that's been freed and the memory poisoned, or just things that aren't correctly initialized. And if I start up the debugger, you can see I've defined several instances of this. I'll just step through. The good value has a correctly initialized canary, and you can see it's got the data in the canary. The no canary value, the programmer forgot to initialize the canary, so it's just 0 because we're using designated initializers. And bad canary, well, the canary's bad. That does not look right. But it's kind of not obvious from here, and it's also a bit verbose. So what we can do here is source in the pretty printer, and I'll show you in a moment, but just want to show you how it's going to summarize this data. So now when we print the good value, it's actually just showing us the data value. It's not bothering to show us the rest of the struct. If we print the no canary value, it's actually done some pre-checking on the canary, and it's warning us, whilst it's showing us the data, that the canary's unset. So we know there's something funny going on immediately. And if we print the bad canary value, then we can see it's identified this as corrupt because the canary's wrong, and it's showing us both the canary value and the data, so we can go figure out what's up. It's worth just noting at this point, if we didn't want pretty printing, we can always ask for raw printing. So if I want to see the bad canary in the default GDB form, E/R, and we can immediately see what we usually have viewed. Now I'll switch across to the Python so you can see how this is implemented. It's pretty simple. We've got the same basic initialization here. We're taking the value in the constructor. But our toString method is a bit smarter. So this is now extracting the data value and the canary value out. And we've got a simple if statement, and it returns different formatted strings depending on what the canary told us. So this is our mechanism for conditionally returning different information to the user. The other thing that I'd like to show is a slightly more sophisticated data structure. Because the other thing that pretty printers are really useful for is showing us kind of large aggregates of data without having to manually walk them on the command prompt. So I'm going to start by showing you another little program. Again, Tui Mode, always useful for this sort of example. Our programmer here has defined a singly linked list that's storing mappings of input numbers to their squares. And we're going to calculate this square of the first 10 natural numbers starting at 0. And actually, we're inserting each new square at the head of the linked list. So we're going to end up with a reversed list of the first 10 square integers. Now, if I run through this, start the process, when we start off, squares is null as an empty list. If I go through one iteration of the loop, you can see it's now pointing to one of our allocated entries. And if I actually print what it's pointing at, we can see we've got the details for the square of 0, which is not that interesting, but we're only one iteration through. I'll just use the until command to skip our way out of the loop. So now the loop's finished its iteration, we should get a little bit more interesting structure in our list. So if I now print the head of the list, you can see we've got the mapping for number 9 to its square 81, which looks fine. If we wanted to see what else is in the list, well, we can do star squares arrow next. We've got a mapping of 864. We can keep doing this ad infinitum. And obviously here, I've got the loop, so I know how many items there are in the data structure. But in the general case, somebody might have just handed me this structure. I don't know what's in it. I want a quick way of seeing without having to sit here typing next, 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 next. So, Pretty Printer to the rescue. I'm actually going to show you the Pretty Printer up front in this case, and then I'll show you the effect it has. So, what we've got here, again, slightly more complex, but not too bad. The boilerplate at the bottom for the regex collection Pretty Printer is basically the same as the other examples, so we can skip that. You can see the init method is still just a very simple mechanism to stash the value we're going to print. That's all good. Our toString method has actually got simpler now. All it's doing is just printing out the type and where it is, and it's not really doing anything interesting. But we've gained a couple of new methods on this object, which tell GDB that it needs to be more clever. First one of interest is children, and this is telling GDB that the thing it's printing is some sort of container. It's got some sort of data within it, and that it needs to iterate through and print all of the elements of. We've got a loop here, which is yielding values for everything in the list, and it'll keep doing that till it gets to the end. We also have this method display hint. And what the display hint's doing is it's telling GDB the thing that's a container is something like a key value map, so please render it like that. If I source this into GDB, we can see the effect this has on printing our list. You can see it's now being displayed in GDB's format for a key value map. So keys on the left in square brackets, values on the right. If I take a subset of the list by indexing into it, you can see that we're iterating through the subset of the list by squirting through all of the remaining links. And it's much easier as a developer to see this. As before, you can disable the pretty printing if you ever want to look at the raw data. But it's also worth saying that pretty printers, a powerful feature of them is you can actually ship them with a library. I won't try and describe exactly how you do this, but you put it in a predictable location or add some information to your compiled binaries, and downstream users of the library will gain access to the pretty printer. So an example of where you might use this is if you're writing a wrapper class, say maybe a C++ kind of like custom string implementation. Your downstream users probably don't want to be debugging your library, so they don't actually want to see when they print an instance of your string, a whole implementation of this is the heap we're allocating on, this is the reference count for this string, etc., etc. They want to just see something in quotes which has got some text in. So what you can do is, with your library, ship a pretty printer that will render your string class as text in the expected way, and your end users then don't have to see the internals of your library unless they want to. So this can be quite powerful if you're trying to ship something, and I believe the standard GNU C++ and possibly libc as well do actually ship pretty printers for some of their data structures, and we are benefiting from them day to day because they're generally installed with the developed packages on people's systems. So that's all for Python from me for now. We are going to have some more examples coming up, but I'll just turn back over to Anastasia for any more questions we might have got, and then we'll hand back over to Greg.
Yeah, thank you. That was just an amazing demonstration. So there is actually a question on GDB/Python. So if it's a valid method for automated white box and or unit testing.
Yes.
From your perspective, how you see that?
I think this is potentially very useful, actually, because you can script things arbitrarily. If you want to inject data values or call a function repeatedly with different arguments, or even perturb some state, you can totally script that up, run something under GDB, and be using GDB as a kind of test and fault injection harness. And if you want to get sophisticated, you can also start making assertions about the internal state of the program, because you can access all of it.
Yeah, that's true. And maybe one more quick question here at this stage. So actually, like GDB using Python. So how much Python should I actually learn to, utilize GDB and, these Python features properly?
So you've got the full Python interpreter there. So the more Python you learn, the fancier the code you can write. But I'd actually say, to get the benefit of it, if you can gdb.execute to run commands, parse and eval to get data, and if you can do loops, print statements, and conditionals, you can probably already do some pretty cool stuff, actually. Even things as simple as please just run the sequence of GDB commands n times is going to be quite easy to implement once you've got that level of basic Python.
Great, sounds great. Thank you. Okay, now let's move back to Greg. Greg?
Yeah, great. Okay, so I was going to show you a demo of how we can actually make our own Tui windows using the Python that Mark's just been showing, but we're a little low on time. So I'm just going to say that you can do that. You can make your own Tui window display now using the Python integration of GDB. Is every version of GDB comes out, it gets tighter and tighter, and you can do all kinds of amazing stuff with it. But let's move on, because there are a lot more to GDB than just the Python. And we're going to talk about reversible or time travel debugging, and really answering this question: how did that happen? Right. So when we're debugging, the process is we expected the program to do something, and reality was different from our expectation. And the process of debugging is to find out where exactly did reality diverge, right? And often I've got often millions of lines of code. Any modern computer is doing billions of things every second. So it really is, as we were saying earlier, that ultimate kind of needle in a haystack challenge, trying to find out what's going on. And particularly the nasty bugs. Well, there are two things that make bugs really nasty. One is, how long is it between the bug itself, the bad line of code, and you noticing, right, the assertion fails or the program fails or whatever. And the longer that gap is, the harder it is to debug, right? And then the other axis on this plot of how hard bugs are is how deterministic is it? Does it always fail in the same way? When programs fail in different ways, or they only fail one time in 1,000 or something, or every time they fail in a different way, particularly hard, then these just get really, really hard to debug. And the debuggers, most debuggers that just let you step forwards in time, it's kind of almost the opposite of what you want to do. What you want to do is answer the question, what happened? What just happened? How did I get here? Right? And that's what time travel debugging will let you do just kind of straight away. So GDB has inbuilt time travel debugging, reversible debugging in GDB speak. It does work, although it's very slow. There are things, we'll come on to things you can use to make that a bit better, but I'm going to show you the concept here first of all. So here I've got a very whoops, where's it gone? Very simple bubble sort implementation. It doesn't do anything really. It just gets an array, randomized array, and then runs a bubble sort on them. Okay, and that's just a run it program here. It doesn't output anything. It just runs. But I happen to know that this. I run it in a loop like this, I know that eventually, if we let it run long enough, it will fail, because this has got an intermittent, rare bug. So it's running a whole bunch of times. Now, demos with these seldom failing bugs are always a bit tense, because you kind of think it is. There we go. It's died, right? So let's have a look. So I can look at the core file, perhaps. So core file dumped y. Oh, I don't know where has it put that core file. That wasn't what I expected.
I bet your fancy new distro squirreled it away somewhere.
Yeah, it's in my core pattern somewhere. How do you find that? Do you know, Mark, core pattern?
I think it's going to be proxys.
Proxys.
A process kernel core pattern.
Right, there you go. Oh god, it's that apport thing. I think I can do service apport stop. Oh, I'm not going to do this because that's going to just take forever to run again. So take it from me that core file is not going to be helpful because it's a stack smash bug. Right, so look at my core file. I'm going to see just garbage. So again, those core files are often the best you can do at finding out how did I get here. I can look at a backtrace, but if my stack is smashed, that doesn't work. So I'm going to do it this way instead. I'm going to load up that program into GDB. Okay, here we go. And of course, when I run it, actually, just to show you, of course, usually it runs to completion, right? So that's not very helpful. I need to run it a bunch of times, and I'm going to run it with process record so I can see exactly what's happened. So what I'm going to do, and this is going to show a few GDB tricks all at once here. So we're going to put a break on main, and I'm going to put a break on exit. So if it exits cleanly, it goes through the underscore exit library, right? A library function. And I'm going to attach some commands to these breakpoints. So on breakpoint 2, I'm going to tell it to enable recording and then continue. And on breakpoint 3, which was the underscore exit, I'm just going to tell it to run again. Now, the other thing I'm going to do is set confirm off, because you'll see why in a moment. I'm going to set pagination off, you'll see why in a moment. So now when I run it, it pings through each time, right? So when it gets to exit, what it's doing is just starting again. And when it gets to main, it's enabling recording and running through. You can see it's kind of slow, right? I mean, this runs, when I was running it, normally it was running, like filled the screen up straight away, right? So it was running at least hundreds of times a second. And now it's running about once a second. But that's okay. Oh, look, now it's stopped, right? So now I didn't hit the second breakpoint, the underscore exit breakpoint. The error message it gives me is kind of a bit kind of confusing, but ignore that for a moment. So if I was looking at my core file, this is what I would have seen: garbage and garbage backtrace. I can look at, so where am I? Print program counter. Okay, I'm here. So let's have a look at the memory. Examine the memory at that address. Oh, there isn't. So my program has branched to an invalid address, probably because I got garbage on my stack. So what I'm going to do here is reverse step I. So step I, as you probably know, steps you forward one machine instruction. Reverse step I is going to step me backwards one machine instruction. Okay, now look, this looks hopeful. If I go layout source, we can see, yeah, look, I'm at the end of this this function. So it does look like I've returned into hyperspace. I can disassemble the current function just by typing disassemble, and it shows me this line here. This little arrow here tells me where I am, and yeah, I'm at a return instruction. So return on x86 will take whatever the stack pointer points to, so and branch to that. So print stack pointer. So that's my stack pointer. So if I examine the memory at the stack pointer, that's looking kind of familiar. Remember that? That's where the program counter was, wasn't it? So sure enough, I've got nonsense on my stack. So who wrote into my stack, right? This is memory corruption, always a hard thing to track down. Well, I'm going to use a watch point. I'm going to watch void star of that stack pointer value. And I'm watching the memory of that stack pointer address. And now I'm going to reverse continue. So I expect you probably know about a watch point, right? If you don't, watch point's kind of cool. You watch an expression, you continue the program until the end, and the debugger will stop when that expression changes. But when I reverse continue, I'm going to go back in time until that watched value changes, until that location on the stack was most recently written. And that is probably the line of code that has corrupted my stack, right? So here we go, reverse continue. Okay, I've stopped here. I've stopped at array equals some random value. It's the ith entry of the array, print I. I is 35. That's interesting, because what is array? Array is 32 entries long. So clearly I is out of bounds. How has I come to be out of bounds? Well, I can see here we're modulo size of array, and of course that's the size of the array in bytes, not the array size in entry in elements. So there's the bug. It's a simple stack corruption bug, but it's a good one because it only happens occasionally. It's random, right? And usually it's writing all sorts of garbage over my stack, and 99 times out of 100 I don't notice, right? Because it just happens to I'm quite near I don't have a lot of stack above me. But there I can just use the reverse debugging, the time travel debugging, to see exactly what happened. So if I go back to my slides, right. So that's kind of neat. We also saw the nice ability to cook commands on breakpoints. That's quite useful little feature. Inbuilt GDB reverse debugging, as I say, is very, very slow, like tens of thousands of times slower than running the program normally. If you've got a particular small piece of code you're trying to understand, it can still be useful, as we've seen in that example. It also doesn't support some of the newer sort of SSE type, the newer AVX type instructions. But when it works, it can be useful. There is an inbuilt but recalled Btrace, which will use the branch trace or the Intel processor trace if they're available. Unfortunately, on my machine, if I try to use it, if I go, I think I can I stop recording? Yeah, we can record. And then I can go record Btrace. Unfortunately, oh, hang on. That's interesting. When I tried that before, it told me the CPU wasn't supported, and then it likes it. That's very weird. Why did that happen?
I think you're still in replay at that point, Greg.
No, it's working. Don't understand. Bizarre. Anyway, sometimes it works, sometimes it doesn't. Last time I tried it on this machine, it didn't work. Maybe it's a different version of GDB or something. So that's the good news is that's much faster. The bad news is it only works if your CPU supports it. And also, though, it's not really time travel debugging because there's no data. It will just tell you can reverse next, so you can see what instructions ran, but you can't see what the data was. And that's really what you want. Okay, so what you want, when you've got full time travel debugging, you can step back to any line of code that executed, and you can see any piece of data for any point in history. So much better for that is a thing called RR, stands for record and replay. That works really well. It's nice and fast. And it works using a very different method, and so it actually does work on real-world large complex code. But again, it is sort of restricted in certain ways. So you can't run it in AWS because it doesn't have access to the kernel features it needs. It does need certain kernels and hardware in order to run. But if you've got everything you need and your program isn't doing anything like shared memory or async IO or something, then RR works very well and is very powerful. And then there's also, just if you'll excuse the very brief product pitch, so live recorder and UDB, well, that does that. That's the best of all worlds. It's nice and fast, and it works anywhere. So it's and works on whatever your code does. So that's a subject that's close to my heart. Right, enough of the shameless plugging. Let's move on. So let me just see how we're going for time. So we've got. Okay, yeah, we're going to have to go fairly quickly through this. So we're going to just go through little bits of advice, little bits of things just to show you they're there. We're going to go very quickly now. So GDB init, so you can have it in your home directory. You can have a local GDB init for each project. My advice is keep it simple. I only have a few commands in my GDB init. I know people have done things like they add all sorts of things, run and other things in GDB init to try and save themselves some time, and you get into a tangled mess. So keep GDB init simple. Source things so you can source things if you want more complex stuff, and you can check them into your repository easy, and your friends can use them as well. Mark?
You might also want to use a set prompt when you've applied some custom GDB config to remind you that you've done it.
Good thinking.
So another useful feature of GDB is remote debugging. GDB, depending on your distro, might be packaged with GDB, or a separate package has a server which splits the debugging attachment to the process away from the symbolic debugging in the user interface. You can fire up a GDB server on another device, possibly one with more limited capacity, and use GDB on your dev machine with full access to source code and symbol information to debug it.
GDB can debug multiple processes at a time, right? So GDB has this notion of the inferior. Again, confusing terminology, I think, but that's the debuggy, that's the program you're debugging. And just like you can have multiple threads, and you know how, if you debugged a multi-threaded program on GDB, you go info threads and thread 1 and thread 2 to switch between the threads. Well, you can also go info inferiors and inferior 1, inferior 2, and you can actually debug multiple processes at the same time. You can follow across forks. You can create new, clone new copies of your inferior when you want. So that's pretty cool stuff. So yeah, clone inferior command second from the bottom there. That's kind of neat. Yeah, you could just be debugging multiple processes in a single GDB, which, if you've got a multi-process environment, that can be handy.
So another feature, perhaps less often used, but potentially useful, is Nonstop mode. Standard GDB behavior is if any of your threads does something interesting, it's going to stop them all and let you have a good look at it, which is fine. But if those threads are doing something live, like maybe you're debugging a service that has network connections that can time out, that's not ideal. Non-stop mode lets you just stop the thread that did the interesting thing. The other threads carry on running in the background. So potentially you can use that to just inspect part of a running system. You set non-stop on to enable it, and if you want to continue all the stop threads, you now have to do continue -a, otherwise it will just continue the thread you're looking at.
Breakpoints and watchpoints. I'm sure you know about breakpoints. We introduced watchpoints just before, but perhaps more than you might realize. So if you just do watch foo, yeah, it's kind of very powerful, particularly with time travel debugging. But it's actually what you're doing is watching the expression. So if you end up doing, I'll just quickly switch here. So if I go watch foo points to bar, that will actually put two hardware watch points in place, one on foo, one on bar. So if foo moves, it will reset the watch point, right? And also if foo goes out of scope, you exit from the functional block where you currently are, then it's local, then the watch point gets removed. So it's not actually watching the location in memory, it's watching the expression, the value of the expression, unless you say watch -l or watch -location, which will actually watch the memory. So if you're looking for some sort of memory corruption bug, that's probably what you want. You can have read-only watch points or a watch actually for read-write watch points. You can have thread-specific watch points, or you can have conditional watch points, and the same for breakpoints too, thread-specific or conditional breakpoints.
So, as previously covered, you can select which thread you're working on in GDB using a thread command. Thread followed by an ID. That's the ID returned by info threads, not the TID, which is an operating system specific idea. You can also ask the thread command to carry out another GDB command in a thread for you. So you can say thread apply, give a thread ID or multiple thread IDs, tell it to print the stack pointer, and you'll get the stack pointer for those threads. You can thread apply all to get a backtrace. You can even use this for things like calling a function in a particular thread, and Greg's going to talk more about that.
So yeah, call foo. You've probably seen this. I can call functions in the inferior, not when I'm debugging a call file, but if I'm debugging a live process. It can be very useful for walking data structures and the like. Beware though that sometimes you can end up calling functions by mistake. So if I print foo, open close brackets, it calls the function. Not so surprising. Print foo plus bar. If I'm using C++ and the plus operator is overloaded, then that will call a function in the inferior. Even print erno will end up calling a function in the inferior to get the thread local storage location. So that can be confusing. If I could do this struct copy, call struct copy at the bottom here, that's going to call, obviously, it's not surprising, called struct copy. What might be more surprising is before it does that, it's going to call malloc to allocate some bytes into which to write that literal string. So if you're debugging a custom malloc implementation, as I was once, that's really confusing. Actually, I think the very latest versions of GDB have fixed that, and they don't magically call malloc behind your back, but it still will call inferiors when you might not be expecting it. So just beware of that.
So dynamic printf is another in the family of breakpoint-like things that GDB offers. This is a breakpoint which not only has a source file and line number or function name, but also has a format string. And effectively, you can use this to add printf-style logging to a program after the program's compiled by telling GDB, whenever we get here, please print this. You can configure it. You can configure it so that GDB uses its own printf implementation or defers to one that you've provided. You can set how exactly that stuff's output. Calling back to the question earlier, this is the kind of thing you might want to do as part of some sort of white box testing if you were using GDB and that to log more information out of what the product's doing.
Right. Catch points are kind of super cool. They're another kind of special breakpoint. So I can catch when an exception is thrown, or I can catch when a particular syscall is made. I think Mark talked through some of this, I think, already. Actually, did you mention this?
Haven't.
Oh, no.
Haven't mentioned commands yet.
Yeah.
This I'd say is the other super useful thing that you might want to include in your Python learnings. You define a class that inherits from gdb.command, you instantiate it, and now GDB has another custom command. So I've added a few utility things like decoding weighted statuses, which I just need to do often anyway, as custom commands. They can do anything you can do in Python. It's just convenient when you're in your debugging session.
You can also have Python functions run when certain things happen, like when you stop at a breakpoint or a signal, and a whole bunch of other cool things, temporary breakpoints, regex breakpoints, so you can put a breakpoint on every symbol that matches a regular expression. We already saw commands silent are quite useful for breakpoints that are inside script when you don't want them outputting. Finally, I want to make a point that is often missed. GCC, or same for Clang, -G or -G3, as I did at the beginning, and -O or -O2 or whatever are orthogonal. So you can have optimized debug builds. Most people have builds that are either release builds or debug builds, and it's like full optimization and no debug information all the other way around. -OG is actually useful as an optimization level that's kind of sensible, but will allow a sensible level of optimization and will also allow debugging to work reasonably well. Key point is -G or -G3 or whatever will not change the code that's generated. So you can use it in confidence. It will make your resulting binary bigger, of course, because it's got the debug info, but that's all. That will all stay on disk, unless you're actually debugging it. So, for performance reasons, generally no problem adding that -G. Final point, then, just want to say we've tried to race through loads of stuff, giving you some bit a little bit more deeply, some of it more just to know it exists. There's more in-depth tutorials from me and from Mark on the GDB watchpoint website. So that's as part of Undo.io. There's a picture of me with my dog. He's not nearly as good at programming as he thinks he is. So that's the URL there. Go to Undo.io resources, GDB watchpoint, and you can get little 5-10 minute tutorials that cover all that we've covered today and lots more too. So thank you very much for listening.
Thank you.
Thank you, Craig. Thank you, Mark. That was an awesome talk. I hope our listeners learned a couple of tips. And we actually have some questions, but since we're running out of time, so I guess we'll move all the questions now to the discussion zone. So I encourage everyone to join the discussion in Zoom now. And so thank you for watching, and goodbye to everyone else.
Goodbye.
Bye, everyone. See you on the Zoom, hopefully.